Hello everyone. Today we discuss section 1.1 about sets and functions. So first of all, let's talk about sets. There are different ways to define sets. You can first list all elements in the set. For example, the set one right here. You have the names Elijah, Arad, and so on. So this is a set of names. Another way to define a set is to specify a property that determines all elements in the set. For example, you can define the second set here as follows. Set 2 is the set of students in Math 4350. So instead of listing elements here, you specify a property. And as long as an element satisfies this property, it is a member of the set. So that's why we have many different ways to define sets. Now, let's talk about some notable sets. N is the set of natural numbers. So here you count all the natural numbers, 1, 2, 3, and so on. This is the set, this is called the set of natural number. And Z is the set of integers, 0, 1, minus 1, 2, minus 2, and so on. Also, a set that appears very often is the empty set. The empty set is a set that doesn't contain any element. Now, for elements and sets, there are some relation. First of all, you can define membership. X is in the set A, X is a member of A, and it is denoted by this symbol. And you use this notation to denote Y is not an element in A. So this is how you define membership. Next, you can define whether a set is a subset of another set. So this is a relation between two sets. So B is a subset of A if and only if any element X in B is also an element in A. Here is an example. Let's say you had a set 2 is a set of all students in Math 4350. And then you have the set 3 is a set of all students, Texas Tech. Then definitely set 2 here is a subset of set 3 because a student taking Math 4350 with me is certainly a student of Texas Tech. That's why any element in set 2 is an element in set 3. That's why set 2 is a subset of set 3. Another relation we can define is the equality relation. So A is defined to be equal to B, if and only if A here is a subset of B, and coincidentally, B here is also subset of A. So when these two conditions are satisfied, then we say that A is equal to B. Now, in addition to relation, we can also define several operations on sets. The first operation on sets is union. We say that A union B is a set that satisfies the following property. X is an element in this set, if and only if X is an element in A or is an element in B. So the union here is really the combination of the two sets together. The other another operation is the intersection. So you can define the intersection of two sets, and that is another set. And that set satisfies the following property. An element in this set, the intersection of A would be here, even only it must be in A and also in B. So the intersection is really the set of elements which belong to both A and B. In other words, it is a set of common elements of these two sets A and B. So to understand, to have some visualization about these operations, we use what is called a Venn diagram. So for the Venn diagram here, the set A here uh, consists of part 1 and part 2, and the set B here consists of part 2 and part 3. Then the union of A and B is a set that consists of part 1, part 2, and part 3. And then the intersection of these two sets is just the part 2. That is a common part between these two sets A and B. Another operation between two sets is the complement. So we say the complement of B related to A is a set that satisfies the following property. So it denoted by this symbol, and it satisfies the property that an element in this set, even only X is an element in this set, even only X is an element in A and not an element in B. So in other words, this is a set of elements that only belong to A and not to B. And for example, for the set A and B as above illustrated by this Venn diagram, then the complement of A relative to B is part 1, and the complement of B relative to A is part 3. It is a set that contains part 3 here. And the following is a theorem which basically tells you how these operations are related to each other. For example, if you take the complement and then you take the union, then you have what is called the Morgan law. So you take the union B and C, and you look at the complement of this union related to A, then this is exactly equal to the intersection of B related to A and C related to A. And you have another similar um, equation for the interaction between the complement and the intersection. So let me explain the proof part A here, just to illustrate what we gonna see quite often in this class. So this is an advanced class with special attention to proof. In this class, you will have to construct proof which is which are logical and reasonable. So this is an example of how to write a proof. So in this case, we want to show that the complement of this union related to A is equal to the intersection of these two sets. So going back to the definition of equality, we observe that A equal to B, the two sets are equal to each other if each set is the subset of the other. So applying that definition to this problem, we want to show that First, the complement here is the subset of the intersection, and second, the the by the way, there's a typo here. This one, this would be the union, not the intersection. So let me use another color to emphasize this is the union. Okay. And so for the first part, we consider an element X inside this set, which is the complement of the union B with and C related to A. So by definition, X is the element in this set if and only if X is an element in A and X is not an element in the union of B and C. That is, X must be in A and X must not be in B, and it also must not be in C. Because the union, remember, that is a combination. So if X is not an element in the union, then it must not be an element in any of these sets. So that's why X here must belong to the complement of B related to A, because it belongs to A and not B. And it also belongs to the complement of C related to A. And together, X here is an element of the intersection of the two sets. And for the second part, we follow a similar line argument, but we start with an element inside the union of the two sets. So X here is in the union, in the intersection. So that's why X must be an element in each of these sets. So that's why X must be an element in the complement of B related to A, and X must also be in the complement of C related to A. So that's why X must belong to A, and it must not belong to B. X must belong to A, and X must not belong to C. Together, we see that X must belong to A, and X is not an element of the union of B and C. So that's why X must be in the complement of the union of B and C related to A. So take a little bit of time to digest the proof, and you're gonna see that the proof here really is just a list of interpretation of definitions that we see in these statements. So in order to prove something, you must interpret what it means, and then you go step by step to deduce the next statement after next statement. And eventually, by using these interpretation and logical reasoning, you gonna arrive at the desired statement. So that is the idea of a proof. And so in summary, the first lecture here is about sets, and we had different ways to define sets. We had several relations. We have some relation between two. We have some. We have some. We have the relation between an element and a set, and also the relation between two sets. And one set could be a subset of other, or the two sets could be equal to each other. We also discussed several operations on sets, such as the union, the intersection, and the complement. And then we look at theorem, Morgan laws, about how these operations are related to each other. And we saw an example of a proof. And the proof here basically consists of interpretation of definition and logical reasoning. And that's it for the first lecture.